In the boundless darkness of space, giant spirals of light are born. Why do they take this particular shape? What holds them together for billions of years? And why does this order eventually break down? Spiral galaxies are among the most enigmatic structures in the universe. Nearly 70% of all known galaxies follow this pattern. But what dictates this order? Gravity? Dark matter? Or something we've yet to explain? These colossal vortices of stars, gas, and dark energy rotate with astonishing precision. Yet the hidden dynamics of their existence continues to baffle scientists. Let's delve into the depths of space and attempt to unravel the mystery behind their mesmerizing symmetry. To begin with, let's answer the question of what exactly are spiral galaxies? The answer is relatively straightforward. Spiral galaxies are systems with well-organized arms, visible clusters of stars, and concentrations of interstellar gas arranged in a disk. Despite their frequent occurrence, the processes that lead to their formation and maintain their structure remain a subject of ongoing debate. Spiral galaxies exhibit a wide range of structural variations. Some systems display well-defined symmetrical arms known as grand design spirals, while others appear more fragmented, with multiple arms that are difficult to count. Some galaxies also feature a central bar from which spiral arms extend. The formation of these barred spirals suggests that internal dynamics can differ significantly from one galaxy to another. Moreover, the color distribution within spiral galaxies provides insight into their stellar populations. In some galaxies, the arms are dominated by younger, hotter stars that emit light in the blue part of the spectrum, while in others, older, redder stars are more prevalent. These differences indicate varying histories of star formation and distinct underlying conditions within the galaxies. Additionally, some galaxies that initially appear to be spirals may exhibit unusual features due to interactions with neighboring galaxies. In cases like this, gravitational encounters or minor mergers can distort the spiral pattern or even result in hybrid characteristics not observed in isolated systems. Historically, these objects were first identified as spiral nebulae in the mid-19th century. Early observers recorded their shapes without fully understanding their distances. In the 1840s, one of the first astronomers to note their distinctive spiral form was William Parsons, 3rd Earl of Rosse, who observed an object later named Messier 51. At the time, these objects were not recognized as full-fledged galaxies, but were instead considered isolated patches of light, and the term nebula was used for any diffused astronomical object. Nearly a century later, in the 1920s, a breakthrough occurred when observations confirmed that these nebulae were not part of our galaxy, but rather separate islands of stars. This revelation, largely thanks to the measurement and keen insights of Edwin Hubble, fundamentally changed our understanding of the universe. Recognizing that these spiral structures existed beyond our own Milky Way expanded the cosmic scale in which we situate ourselves, proving that our galaxy is just one of many. However, following these early milestones, science encountered a major challenge known as the winding problem. when it was discovered that stars in a galaxy do not rotate as a single unit, but move at different speeds depending on their distance from the center, it begged a perplexing question. If all matter in a spiral galaxy rotates at varying speeds, why don't the arms wind up tightly and disappear over time? Early theories suggested that galaxies might rotate as solid bodies. However, further research revealed that stars closer to the center complete their orbits more quickly than those on the outskirts. This differential rotation led to the expectation that over billions of years, the arms should become tightly wound, contradicting what we actually observed. Instead, the arms remain relatively open and stable, raising a fundamental question about the mechanisms that preserve their structure. Several theories have been proposed to address this issue, each attempting to explain both the formation and persistent existence of spiral arms. One of the most well-known explanations is the density wave theory introduced in the 1960s. According to this model, spiral arms are not material structures in the conventional sense, but rather regions of increased density that move through the galactic disk. As stars and gas pass through these regions, they experience a temporary increase in density, triggering star formation. The co-authors of the theory compare this effect to a traffic jam on a highway, where the flow of vehicles slows down but individual cars continue to move forward. While this model explains the symmetry observed in many spiral systems, it leaves unanswered questions about the origin and sustained nature of these waves. An alternative explanation considers a mechanism based on self-propagating star formation. According to this point of view, new stars form in denser gas regions, and subsequent shock waves from supernovae trigger further star formation in neighboring areas. This chain reaction can lead to the formation of loosely organized spirals. The resulting structures, often called flocculent spirals, are less symmetrical and stable than those explained by density waves. While this theory accounts for the patchy appearance of some spiral galaxies, it fails to adequately explain the highly regular grand design spirals observed in most cases. The third theory, known as swing amplification, suggests that small perturbations in the disk, possibly from collisions between gas clouds or gravitational interactions with nearby objects, can be significantly amplified by the galaxy's differential rotation. These small initial disturbances can grow into well-defined arms. While oscillation amplification can lead to noticeable features, simulations indicate that the resulting arms may be transient unless continuously reinforced by additional perturbations. Thus, this theory links spiral arm formation to the inherent instability of a rotating disk, but does not fully explain the long-term persistence of stable spiral patterns observed in some galaxies. When considering these theories, one thing becomes clear. No single mechanism explains all observed spiral structures. Instead, the variety of spiral forms suggests that multiple processes may be at play, sometimes simultaneously. While advancements in observational techniques have provided new insights into spiral galaxies, they've also introduced new challenges. Astronomers now rely on multi-wavelength observations to study these systems. Optical light observations reveal the distribution of young stars. Infrared observations, on the other hand, can penetrate dust that often obscures the true structure of a galaxy in visible light, while ultraviolet images highlight regions of active star formation. For example, a galaxy that appears to have a well-organized spiral structure in infrared images may look much more fragmented in the optical range. This discrepancy largely results from the different sensitivities of various wavelengths to dust and gas. Dust can obscure older stars while emphasizing regions of recent star formation, complicating interpretations of the underlying structure. In addition to multi-wavelength imaging, spectroscopic studies provide further insights into the movement and composition of stars in these arms. However, interstellar dust absorption and the complex blending of stellar spectra continue to pose challenges for astronomers in their attempts to develop a unified model of spiral structure. Studying spiral structure in galaxies beyond our own has the advantage of providing a clear external view. However, understanding the architecture of the Milky Way presents a unique set of difficulties. Being inside the disk, observers cannot see the Milky Way in its entirety. Determining the number and configuration of its spiral arms remains a topic of ongoing debate. Some studies suggest the presence of 4 primary arms, while others argue that only 2 are well defined, with additional structures representing smaller branches or spurs. There's also an ongoing debate about the presence or absence of a central bar. Recent data from space observatories, including the renowned Gaia astrometric mission, have provided unprecedented insights into the positions, motions, and brightness of nearly 1 billion stars. However, even today, processing and interpreting such a vast data set remains a complex challenge, and recent analysis have even called into question some long-established theories about the spiral structure of our galaxy. In such contradictory situations, computational models have long played a crucial role in deepening our understanding of theories. Early simulations were based on simplified models that considered only gravitational interactions between stars. Initially, they supported the density wave theory, suggesting that spiral patterns could naturally emerge under the influence of gravitational forces acting within a rotating disk. However, in recent years, advances in computational technology have enabled simulations that take into account a wide range of factors, including gas dynamics, star formation processes, supernova feedback, and interactions between stars and interstellar matter. These detailed models often produce spiral structures that are transient or unstable, especially when the simulation includes the full complexity of physical processes. Researchers have found that the results of these kinds of simulations can vary significantly depending on initial conditions and model resolution. Simulations with fewer particles may depict spiral patterns as short-lived and disorganized. Conversely, high-resolution simulations with a greater number of particles and more realistic physical processes have shown that under certain conditions, stable, long-lived spiral patterns can emerge. These advancements in modeling have provided valuable insights, but have also revealed the sensitivity of spiral structures to various physical parameters. Turns out a combination of factors, including density waves, local gravitational instabilities, and external disturbances, can all play a role in the formation and maintenance of spiral arms. Modern research suggests that there is unlikely to be a single definitive explanation for the spiral structure of galaxies. Instead, evidence indicates that multiple mechanisms may operate simultaneously or under different circumstances. In galaxies with well-defined symmetrical arms, density waves may play a dominant role, whereas in other systems, localized star formation and different rotation may be more significant. The variations in spiral patterns observed across different galaxies suggest the influence of multiple factors. In some cases, interactions with other galaxies can trigger or modify spiral structures. In other cases, internal processes such as localized gravitational instabilities dominate. The combination of multi-wavelength observational data and complex simulations continues to deepen our understanding, yet many questions remain unresolved. Upcoming missions such as the Nancy Grace Roman Space Telescope and Euclid, along with ground-based observatories like the Vera C. Rubin Observatory and the Extremely Large Telescope, are expected to expand our knowledge of spiral galaxies. These instruments will provide high-resolution multi-wavelength data, enabling detailed studies of stellar dynamics, dark matter distribution, and intergalactic interactions. Over the next few decades, their advanced capabilities are expected to resolve key uncertainties in the formation and evolution of spiral structures. This will also provide crucial data for models attempting to explain the large-scale structure of the universe. Overall, the study of this question goes beyond understanding individual structures. Understanding the processes underlying the birth, maintenance, and disruption of spiral arms is essential, as these structures serve as windows into fundamental aspects of galactic evolution. Spiral arms are not merely decorative features. They're active regions with evident interplay of gravity, gas dynamics, and external influences. This interaction offers clues about the hidden mass of galaxies, particularly dark matter. The formation and preservation of spiral arms are strongly influenced by gravitational potential, which is largely determined by the dark matter halo. By analyzing the dynamics of these arms, how they twist, strengthen, or dissipate, astronomers can indirectly determine the distribution and density of dark matter. Furthermore, spiral arms are key regions for star formation. As gas clouds pass through these arms, their density increases, leading to gas collapse and subsequent star formation. Thus, the arms serve as excellent laboratories for studying the efficiency of star formation. Understanding the conditions that promote or hinder star formation helps scientists construct a comprehensive picture of how galaxies grow and change over time. Additionally, the structure of the arms often bears the imprint of past interactions. Tidal forces from neighboring galaxies or remnants of minor mergers can distort or trigger the formation of spiral patterns. This historical perspective is crucial, as these interactions affect not only visible structures, but also the distribution of baryonic and dark matter. In the meantime, each new observation refines our cosmic map and deepens our understanding of the universe, gradually unveiling its mysteries one step at a time.